Hi, this is Owen Astrachan with Video U, Greedy Algorithms for CompSci 201, academic year 2021-2022. U is for Unix. That is the basis for Linux, the basis for Android, the basis for GNU, and so many other operating systems. U is also for user interface, which is UI, and user experience, which is UX. In both cases, the user is the heart and soul of that aspect of software design and software engineering. In this video, we're going to discuss greedy algorithms. And before we define greedy in a more precise way, I'm going to use an example that's the perhaps prototypical example of a greedy algorithm, which is making change with the fewest coins possible. And in general, as we'll see, a greedy algorithm is trying to solve an optimization problem, doing something with the most or the fewest. And in this case, we want to make change with the fewest coins possible. And with US coins, and in the coinage system of many countries, the greedy algorithm says to make change with the fewest coins possible, simply take the largest denomination coin and then see how much change you have to still make and continue taking the largest denomination coin. So for example, if we are going to make change for 32 cents and we have quarters, dimes, nickels, and pennies, as we do in the United States, then first we choose the largest coin. That's a quarter. We would need to make change for 7 more cents after taking 25 away from 32. To make change for 7 cents, we'd use a nickel. That's the largest coin that we have available to make change for 7 cents. That would leave 2 cents left and would use a penny and another penny. So we would have 4 coins for making change for 32 cents, and that's the fewest coins possible. Suppose, however, we're in an old-fashioned cash register and we've run out of nickels. So what we have is quarters, dimes, and pennies. If we use the greedy algorithm, first we'd choose a quarter to make change for 32 cents. Now we'd have 7 cents to make change for, but we're out of nickels. So we would have to use 7 pennies. And the greedy algorithm of choosing the largest denomination coin we can would yield 8 coins, a quarter plus 7 pennies. But we can do better than that. To make change for 32 cents, instead of 8 coins, we could choose 3 dimes, 30 cents, and 2 pennies. That's 5 coins. That's fewer than 8. So there we'd need a non-greedy algorithm. And in general, greedy algorithms sometimes work and sometimes don't. And in some courses, as we'll see, if you continue in computer science, you might prove that the greedy algorithm is optimal. Because in greedy algorithms, we're trying to solve an optimization problem. Do something with a maximal or minimal amount. And you make a choice that looks good locally. In the coin example, we choose the biggest coin. That's a local decision. But it leads to a global optimum where for all the change we're doing, we have the fewest coins possible. The local choice is the local biggest denomination coin right now, and it leads to the global optimum. And if you take more courses, you'll prove that some greedy algorithms are optimal, but not all are. One greedy algorithm that we'll see later is Dijkstra's shortest path algorithm, which is used to find the shortest path between 2 points, 2 towns on a map, 2 places on the internet that need to be connected. So Dijkstra's algorithm is ubiquitous. It's efficient and it's simple to implement because it's greedy and it works in a variety of applications. Huffman coding, which is the ultimate last assignment in 201, also uses a greedy algorithm, as do some spanning tree algorithms, minimal spanning trees. And we'll see that when we look at graphs. So greedy algorithms are often used to solve problems in computer science. I'm going to discuss an example that you'll see in a later APT, which is the Olympic candle example. In this problem, which is a standard APT that we do in 201, and you can see the URL here, you are given the heights of n candles. So in the example shown here, we have 1, 3, 2, 5, 4, 1, 2. Those are different candle heights. Candle heights are given in inches. And what we need to do is we have on the first night, we burn 1 candle. It shortens it by 1 inch. On the second night, we burn 2 candles. They're each shortened by 1 inch. On the third night, we burn 3 candles. They're each shortened by 1 inch. So some candles are growing shorter, and we continue until we don't have enough candles to burn. If we could burn candles through the 6th night, on the 6th night we'd have to choose 6 candles, each of which is at least 1 inch high, to be able to burn them. So the question is, given some candle sizes as input, how many nights can we burn candles? So there's an example at the bottom of the slide that says, suppose we have 3 candles of height 2. On the first night, we burn 1 of them, so we have a 1 inch candle and 2 2-inch candles. Then we pick one of the 2-inch candles. We now have a 1, a 1, and a 2. Then we can burn all of them, so we have 2 candles that are burned out and 1 candle that has 1 inch left. But we could burn candles for 3 nights. We only have 3 candles, so we can't burn for more than 3 nights. In general, how do we solve this problem? On the first night, which candle do we choose to burn? On the nth night, which n candles do we choose to burn? And I hope that as you're thinking about this, you might see, I should choose the largest, the tallest candles on any night. On the first night, burn the largest candle, because then it will be 1 inch shorter, and you can't really do better than that. And you could prove this, but it turns out that this is the best algorithm, the optimal algorithm. Choose the local, greedy tallest candle, burn it, and then repeat. So, for example, if we have an input, which is the candle sizes, and in this example we have 5, 2, 2, 1, so 4 candles, and we have to burn a candle on the first night, we would choose the 5-inch candle, burn it, and now we'd have a 4, a 2, a 2, and a 1. Now we have to choose 2 candles on the second night. We choose the 4 and the 2. That would yield 3, 1, 2, 1. We've burned candles for 2 nights. On the third night, we have to choose 3 candles. So we would choose the 3, the 2, and the 1, the 3 largest. And that would mean the 3 is now a 2, the 2 is now a 1, and the 1 is now a 0. So these are the candle heights we have left after 3 nights. We can't burn 4 candles on the 4th night because one of the candles is gone. Its height is 0. So we can't burn candles on the 4th night. The return value for the method, given this input, would be 3. We can burn candles for 3 nights. In general, how do we determine which candles to burn? We've said that we want to burn the largest n candles. On the first night, the first largest. On the second night, the 2 largest. On the third night, the 3 largest. One simple way to do this is, before we're going to burn candles on any night, we sort them. Now, when we use timsort or collections.sort, arrays.sort, that's an n log n sort for n candles. Now we're going to do that on the first night, the second night, the third night, the 4th night, and in general on perhaps n nights. So that's n times n log n. That's n squared log n. How does that work? Well, we have the input candle sizes and we sort them. So in this example, I have 2, 2, 2, 3, 11, 12, 15. That's 7 candles. We sort them, and then on night 1, night 2, night 3, and night 4, we choose the largest, the last candle on the first night, the last 2 candles on the second night, the last 3 candles on the third night. So for example, on the second night, the indexes are index 5 and 6 after we sort them, because we have 7 candles. On the third night, we choose the largest 3 candles. That's indices 4, 5, and 6. The numbers will have changed because we will have burned them, but the indexes won't, because we will resort the candles every time. And we can see that we run this for loop that says night is 1, night is 2, night is 3, up to and including the length of the array. We could burn candles for 7 nights. We sort the array, and then we choose the largest n. And the way that code works is, since we're sorting each time, then we choose the last night candles. And so since night is going 1, 2, 3, 4, and NC is the length of the array, the maximum number of candles, we can see that this loop starts at the largest index, NC minus 1, and goes down to the 9th candle. And what we do is we take each candle, and as long as there is a candle there that's of height greater than 0, we burn that candle 1 inch by subtracting 1 from it. And if there is no candle there, that means we cannot burn candles on this night, and so we return night minus 1, because we know we could burn them on night minus 1, and now we're in the next iteration of the loop. If we can burn candles on every night, the loop exits and we return the length of the array. We could burn a candle on every night. That's a simple, greedy algorithm. Whenever we have to find the largest in a collection, we can also use a priority queue rather than sorting everything. And you saw that, for example, in the autocomplete assignment. Rather than sorting all entries to find the top M, we'll use a priority queue. And we can do that here as well. We need the n largest, first largest on the first night, second largest on the second night. We'll see that with Big O, the runtime doesn't change using a priority queue, but it actually is more efficient. And in another APT problem, it will be more efficient in terms of Big O. We're going to create a priority queue, and we're going to create the priority queue with a reverse order comparator, because we want the priority queue to return the largest element when we remove one. Recall perhaps that by default in a priority queue, calling remove gives us the smallest element. But if we change the comparator with which the priority queue is constructed, we can arrange for the largest element to be removed. So we've created a priority queue with a reverse comparator, and then we store all the integer values in our candle array into the priority queue. Now we're set up to solve the problem. We have to loop over the int array parameter candles. We can't use arrays.asList because it's an array of primitive types, not an array of objects like string. Then we go to the next stage of the algorithm, where we're going to iterate for every night, and we remove something from the priority queue that will be the largest candle. If the priority queue doesn't have enough elements, we stop. In the same way with the sorting method, we stop. If the priority queue has fewer than night entries, we don't have enough candles to burn. Otherwise, what we do is we create an array list where we're going to put the candles we burn. We'll discuss why we need to do that. And then we remove the largest candle. Remember, it's a reverse comparator. So pq.remove is the largest candle. We subtract 1 from it, and if there's still a candle left, so after burning an inch, if there's a candle, we put it into the array list that we created before the loop. And we continue this process of taking an element from the priority queue, burning it, and adding it to the array list. When we're done, we will add all the elements from the array list, which are all positive heights, because we only put positive candle heights in the array list. We will add them all back to the priority queue. We can't simply take a candle, burn it, and put it back in the priority queue. We need this external array list because the way the problem is stated, we must burn 1 candle on a night. We can't burn it twice. We can't pick the largest candle, burn it an inch, and then burn it again. So if we put it back into the priority queue, we might pull it out again. So when we take a candle out of the priority queue, we have to set it aside in this array list. And we continue that process, and when we set them all aside, so we've burned all the candles we need to on a specific night, then we put them back in the priority queue. This algorithm is based on the runtime of a priority queue, which is log n. And since we're going to solve a problem on the first night, the second night, the third night, on the first night, we only remove 1 element from the priority queue. That's log n. On the second night, we have to remove 2 elements. That's 2 log n. On the third night, we remove 3 elements, log n, log n, log n. On the last night, if we get there, there will be n candles, n heights in the priority queue. We remove them all. Each one is log n, and we removed n of them. If we do some algebra on this equation, we'll see that we can factor out the log n, and we have 1 plus 2 plus ... n times log n. You know that formula with big O is n squared. So big O, we have n squared log n, the same as the sorting algorithm. However, the sum of the numbers from 1 to n is n squared over 2 plus n over 2. It's n times n plus 1 over 2. So that over 2 means it's half as long for this algorithm. It's perhaps twice as fast as the sorting algorithm, because in the sorting algorithm, we always sorted all the numbers. Here, because it's a priority queue, we can leverage that and get slightly better performance in the real world, but asymptotically with Big O, it's the same. This is Edsger Dijkstra, who was a master of both theory and practice. He created the Dijkstra's shortest path greedy algorithm. He wrote an influential computer science education paper called Goto Considered Harmful. And although he was extremely influential, both in theory and practice, and he had good things to say about teaching, he wasn't always the nicest person. Here's his quote: "For me, the first challenge for computing science is to discover how to maintain order in a finite but very large discrete universe that's intricately intertwined. And the second, but not less important challenge is how to mold what you have achieved in solving the first problem into a teachable discipline. It does not suffice to hone your own intellect. You must teach others how to hone theirs. The more you concentrate on these two challenges, the clearer you will see that they are only two sides of the same coin. Teaching yourself is discovering what is teachable." Enjoy your computing.